The universe operates by a strict set of rules. These rules are not arbitrary, they are the fundamental principles that govern the behavior of everything in existence. From the tiniest subatomic particles to the vast sprawling galaxies, these laws are the invisible threads that weave the fabric of our reality. These rules govern everything from the smallest particles to the largest galaxies. They dictate how particles interact, how stars are born, live and die, and how galaxies form and evolve over billions of years. Without these rules, the universe would be a chaotic and unpredictable place, devoid of the order and structure we observe. One of the most fundamental rules is the speed of light. This speed is not just a measure of how fast light travels, it is a cornerstone of the laws of physics. It is the ultimate speed limit, a boundary that cannot be crossed by any object or information in the universe. This speed, approximately 299,792,458 meters per second, is the ultimate speed limit in our universe. This precise value is not just a number. It is a fundamental constant that plays a crucial role in the equations that describe the behavior of the universe. It's not just a good idea, it's the law according to Einstein's theory of relativity. This theory, proposed by Albert Einstein in the early 20th century, revolutionized our understanding of space, time, and gravity. It provided a new framework for understanding the universe, one that has been confirmed by countless experiments and observations. Einstein's theory, a cornerstone of modern physics, revolutionized our understanding of space, time, and gravity. It introduced the concept that space and time are not separate entities, but are intertwined in a four-dimensional continuum known as space-time. This idea has profound implications for our understanding of the universe. It tells us that space and time are intertwined, forming a four-dimensional fabric called space-time. This fabric is not static, it is dynamic and can be warped and stretched by the presence of mass and energy. Massive objects like stars and planets create indentations in this fabric, which we perceive as gravity. This fabric is not static, it can be warped and stretched by massive objects like stars and planets. The more massive an object, the greater its influence on the surrounding spacetime. This warping of spacetime is what causes the phenomenon we experience as gravity, drawing objects towards each other. One of the most profound implications of Einstein's theory is that nothing can travel faster than light. This speed limit is not just a suggestion, it is a fundamental constraint imposed by the nature of spacetime itself. As an object approaches the speed of light, the laws of physics dictate that its mass increases without bound. As an object approaches the speed of light, its mass increases infinitely, and it would require an infinite amount of energy to accelerate it further. This means that no matter how much energy we put into accelerating an object, we can never make it reach or exceed the speed of light. This creates a natural barrier that cannot be overcome. This effectively creates an impenetrable barrier, preventing us from exceeding this cosmic speed limit. This speed limit is not just a restriction on our ability to travel quickly, it is a fundamental aspect of the universe that shapes the way we experience reality. The speed of light is not just a limit, it's a constant that underpins the very fabric of our reality. It is a key component of the equations that describe the behavior of the universe, and it plays a crucial role in our understanding of space, time, and energy. It dictates how fast information can travel, how we perceive time, and the fundamental laws governing the cosmos. The speed of light is woven into the very fabric of the universe, influencing everything from the behavior of particles to the evolution of galaxies. But what if we could break this seemingly unbreakable barrier? What if there were ways to circumvent the speed of light, allowing us to travel vast distances in the blink of an eye? These questions have fascinated scientists and science fiction writers alike for decades. What if we could journey through the cosmos at speeds that defy our current understanding of physics? Such a breakthrough would revolutionize our ability to explore the universe, opening up possibilities that are currently beyond our reach. While this remains a speculative idea, it continues to inspire and drive the quest for knowledge and discovery. The speed of light stands as an imposing barrier, a cosmic speed limit that has fascinated and frustrated scientists for over a century. This limit is not just a theoretical construct, it has profound implications for our dreams of interstellar travel, shaping the very way we think about exploring the cosmos. To comprehend the magnitude of this challenge, we must delve into the heart of Einstein's equations, which form the bedrock of modern physics. These equations are not just abstract symbols, they describe the fundamental nature of reality. Einstein's theory of relativity reveals that as an object approaches the speed of light, its mass increases exponentially. This isn't just a small increase, it's a dramatic, overwhelming surge in mass that makes further acceleration increasingly difficult. Imagine a weightlifter struggling with heavier and heavier weights. As the mass increases, the effort required to lift it becomes almost impossible. This is analogous to what happens as an object nears the speed of light. In practical terms, as an object accelerates closer to the speed of light, it requires increasingly more energy to continue accelerating. This is why particle accelerators, which propel particles to near-light speeds, consume vast amounts of energy. At the speed of light, the object's mass, and therefore the energy required to propel it, would become infinite. This is not just a large number, it's an unachievable infinite amount of energy. This infinite energy requirement is not merely a technological limitation, it's a fundamental constraint imposed by the laws of physics. No amount of technological advancement can overcome this basic principle. It suggests that exceeding the speed of light would require a paradigm shift in our understanding of the universe. We would need to discover new physics that fundamentally changes our current models. While we haven't completely ruled out the possibility, current scientific knowledge suggests that faster-than-light travel remains firmly in the realm of science fiction. Our favorite sci-fi stories inspire us, but they also remind us of the vast gap between imagination and reality. However, the human spirit is not easily deterred. Throughout history, we've faced seemingly insurmountable challenges and found ways to overcome them. The quest for faster-than-light travel is no different. Scientists and dreamers alike continue to explore theoretical loopholes and alternative models of physics that might allow us to circumvent this seemingly insurmountable barrier. Concepts like wormholes, warp drives, and quantum tunneling are being studied with great interest. The pursuit of faster-than-light travel is a testament to our boundless curiosity and our relentless quest to explore the universe's furthest reaches. It embodies our desire to push the boundaries of what is possible and to seek out new frontiers, no matter how distant or challenging they may be. While the speed of light seems absolute, it stands as one of the most fundamental constants in the universe, a cosmic speed limit that nothing can surpass. This limit, approximately 299,792 kilometers per second, is woven into the very fabric of our understanding of physics and the universe itself. However, theoretical physics offers intriguing possibilities for circumventing this cosmic speed limit. These ideas, while speculative, open up a realm of possibilities that challenge our conventional understanding of space and time. One such concept is the warp drive, a hypothetical technology that could distort space-time itself. This idea, popularized by science fiction, suggests that we might one day travel vast distances in the blink of an eye. Imagine a spacecraft that doesn't actually travel through space, but rather warps the fabric of space around it. This would mean that the spacecraft remains stationary within its own bubble of space-time, while the space outside the bubble moves. The idea is to create a warp bubble that compresses space-time in front of the spacecraft and expands it behind. This manipulation of space-time would allow the spacecraft to effectively surf on a wave of distorted space-time, potentially achieving faster-than-light speeds. This concept, while fascinating, is not without its challenges. The energy requirements for creating and maintaining a warp bubble are astronomical, far beyond our current technological capabilities. Moreover, the theoretical framework for such a technology is still in its infancy, with many unanswered questions and potential paradoxes. While theoretically plausible, warp drives remain highly speculative, requiring exotic forms of matter with negative mass energy density, which we have yet to discover. This exotic matter, if it exists, would have properties that are completely unlike anything we have ever encountered. Another intriguing concept is the tachyon, a hypothetical particle that always travels faster than light. Tachyons, if they exist, would revolutionize our understanding of physics and open up new possibilities for communication and travel. Unlike ordinary particles, which gain mass as they approach the speed of light, tachyons would have imaginary mass and would actually require infinite energy to slow down to the speed of light. This counterintuitive property makes them a fascinating subject of study, even if they remain purely theoretical. While mathematically possible, tachyons remain purely theoretical, and their existence would raise profound questions about causality and the nature of time itself. If tachyons were real, they could potentially allow for communication across time, leading to paradoxes that challenge our understanding of cause and effect. These concepts, though still in their infancy, illustrate the boundless possibilities that theoretical physics offers. They push the boundaries of our imagination and challenge us to think beyond the limits of our current understanding. While we may not have the technology to manipulate space-time or harness tachyons today, these ideas push the boundaries of our imagination and inspire us to continue exploring the universe's most profound mysteries. The pursuit of these concepts drives scientific inquiry and fuels our quest to understand the cosmos, reminding us that the universe is full of wonders yet to be discovered.